Good afternoon, doctor. So we are from group 19.
Our circuit is a full-adder circuit, which is a fundamental digital logic circuit used to add three 1-bit binary input, A, B, and carry input. The circuit produces two outputs, which are the sum and carry output. The circuit is powered using a 5V DC power supply, which is suitable for all the logic ICs used in this circuit. Switches are used to represent the binary inputs A, B, and carry input. Each switch can be set to high or low, corresponding to the binary 1 and 0. The 74HC86 is the XOR gate IC. In this circuit, XOR gates are used to generate the sum output because XOR output high when the number of high input is odd. The first XOR gate adds input A and B, and the second XOR gate combines this result with the carry input. The 74HC08 contains 4 AND gates. AND gates are used to generate partial carry signal, since a carry is produced when two inputs are high. The 74HC32 is the OR gate IC. It is used to combine the partial carry output from the AND gates to produce the final carry out. Two LEDs are used as output indicators. One LED represents the sum output, and the other represents the carry output. Two 750 ohm resistors are connected in series with the LEDs. These resistors limit the current flowing through the LEDs and protect them from damage. Connecting wires are used to link all components together according to the full-adder logic design and ensure proper signal flow. By changing the position of the input switches, different input combinations can be tested, and the corresponding sum and carry output can be observed on the LEDs.
So we're going to demonstrate our logic circuit to perform the full adder performance. Okay, so we can see this is our design, and firstly we'll connect the positive terminal. This is the 5V terminal to here, and then the black wire represents the negative terminal, which is connected to the ground. Alright, so now the blue one represents the sum carry bit, and then the green one represents the carry output, the bit. So we have used three logic gate in this circuit, which is the XOR gate, as seen as here, and the AND gate, and final the OR gate. Alright, so in this section we have three inputs, which is the A, B, and C. The A is shown here, there's the B, there's the C. Alright, so when we manipulate the number of A, B, and C, will change the color to perform the calculation performance. So we will now, this is for the ABC. Now it's all in one logic, which is the active high. So if we change one of them, let's say the B to 0, now we change it to 0. Okay, you can see the sum become dimmer, and then the carry output still shows still lights on, which represent the 1 and 0. So it's 1 0 because we only have A is 1 and C is 1, so 1 plus 1 is equal to 1 0, and the B is 0. Okay, so now if we remove the A to become 0 also,
Okay, when we switch the AB input to 0, the sum bit will light on and the carry bit will become dim, showing the result of 0 1, which is 0 plus 0 plus 1 plus 1.
Cool.
Showing the result of 0 1, which is 0 plus 0 plus 1 equal to 1. When we switch off all the input to 0, The sum and carry bit or lights off, indicating the result is 0 and 0.
So one of the main problems we faced was there was no output from the IC. So initially we thought the IC was faulty, but after checking the datasheet, we realized that we have forgotten to connect the VCC and the ground pins. So once we wired the power pin correctly, the IC started functioning as expected. Another issue was incorrect logic output. The LEDs were turning on, but the result did not match the truth table. After inspecting the wire, I found that some IC pins connection was incorrect. We solved this by carefully rewiring the circuit according to the pin diagram in the datasheet. Lastly, we experienced unstable output, where the LED flicker or turn on and off randomly. This was caused by loose jumper wire connection. By firmly securing all wires and reorganizing the breadboard, the output becomes stable and reliable.